It's good. Okay, I suggest we continue. So we are very, very happy to have Monica Pate from Harvard, and she will continue the story with, I guess, quantum connections between symmetries and theorems. Please, Monica, go ahead.
Okay. So in the previous lecture, Alok nicely introduced this idea of the infrared triangle, which basically you can think of as summarizing a precise way in which universal behavior of gravitational radiation in the infrared can be understood as, in terms of sort of universal behavior that's predicted by symmetry. And so in that lecture, Alok took a classical approach, and at the end showed you how if you look at the low frequency component of classical gravitational radiation, that this implies this class of symmetries that he introduced at the beginning. And so in this talk, what we'll do is we'll take a quantum approach, and by that, what I mean is that we'll use instead field theoretic techniques and study properties of scattering amplitudes, and see how this sort of same story of sort of a precise equivalence between universal behavior in the infrared and universal behavior due to symmetry arises in this language. Okay, so the outline is sort of going to go in the reverse of Alok's talk, is that we're going to start with soft theorems for scattering amplitudes. So in other words, we're going to start by looking at the universal behavior of low frequency radiation, and in particular, how you derive this in the language of scattering amplitudes. And then we're going to see how this implies a class of symmetries. And so in particular, what we're going to do is we're going to take soft theorems, which are the statements about low frequency radiation in the language of scattering amplitudes, and show how they can simply be rewritten to be ward identities for infinite dimensional symmetries. And upon doing that, the next thing we're going to want to do is we're going to want to identify what those class of symmetries are. So I'm sort of going to give a formal argument about why you can always take soft theorems, which are relationships among scattering amplitudes, and rewrite them formally as ward identities of symmetries, but it won't be necessarily obvious what those symmetries are. And so in this third part, I'm going to explain how you figure out sort of what the physical meaning of these symmetries are. And in the final part, then we're going to do some sort of, you might think of, so maybe let me explain how this relates to the triangle. So this, the beginning part will start with the soft theorems, and we'll show that they're equivalent to ward identities for these asymptotic symmetries. In particular, we'll see that these asymptotic symmetries are the quantum versions of the BMS symmetries that Alok had introduced. And then, so in Alok's talk, this triangle was flipped. So just to connect to this, this was what he was saying was quantum. This was classical, and these were the symmetries. And so roughly speaking, what he was calling memory was this waveform, this universal part of the waveform that you could derive for classical radiation. And we'll see that this plays an important role in thinking about scattering amplitudes. And so in particular, I'll explain how it's intimately connected to infrared divergences that arise in scattering amplitudes from the exchange of virtual soft photons. And sort of a well-known result is that actually if you sum up this class of infrared divergences, well, they set all exclusive scattering amplitudes to 0. And this is a statement that turns out, again, to be related to this class of infinite dimensional symmetries. And so I'll explain the relation, and then I'll actually explain how the symmetries can guide you to a result that gives infrared finite, or in other words, non-vanishing scattering amplitudes. And so sort of just to reiterate, the sort of general picture I want to paint is that, from this perspective, there are a bunch of different sort of universal results that one can derive, and I'll actually review some of this sort of from Feynman diagrammatic language in scattering amplitudes. And what we now understand is that many of these results can be understood or argued from symmetries. And in particular, today I'll be talking about the supertranslations, which are associated to sort of the leading behavior at low frequency. Okay. So as I promised in this seminar, the basic idea was that we're going to take a QFT approach to gravitational radiation. And what that means is that we're going to study scattering amplitudes, and we're interested in gravitational radiation. So we're going to study scattering amplitudes involving gravitons. And in order to get at the behavior of radiation at low frequency, we're going to focus on amplitudes that involve the emission of a low energy graviton. And so, as I said, if you actually study such amplitudes, it's known that they admit some sort of universal behavior. And these are called soft theorems. And in particular, sort of the structure of these soft theorems is that if you take a scattering amplitude, and so here P1 through Pn are just some set of particles, and Q is the momentum of the graviton. And so here Q is proportional to omega. So you start expanding in essentially small q or small omega. Then what you find is that this scattering amplitude and this expansion is in fact related to the scattering amplitude without this soft graviton acted upon by some set of operators. And so there's a correspondence between these terms appearing in this expansion and the terms that Alok derived at the end, or introduced at the end of his lecture. And so in particular, this S0, it was his, roughly HAB -1, and then, this was the HAB log and HAB 0.
Sorry, Monica, quick question. So in Alok's talk, there was this difference between d larger than 4 and d equals 4. So in your talk, which number?
I'm working in d equals 4.
Okay.
Yeah. Right. And when I say that there's a correspondence, I mean that actually, so, it turns out that the leading term is precisely the same, but the subleading terms, which you can roughly think of as probing more detailed aspects of the scattering, can differ in some non-universal terms. And I'm not going to talk about them in detail in the talk, but we can sort of discuss them in more detail maybe after in the discussion section. And so the basic takeaway is that if you're talking about low frequency radiation in the language of scattering amplitudes, they're captured by these soft theorems. And soft theorems are basically universal relationships among different scattering amplitudes, one involving the emission of a low energy graviton, the other one being that amplitude without the graviton, and then there's some factor between them, and you can think of that as roughly the sort of low frequency, it corresponds classically to the low frequency component of gravitational radiation. Right, so here I'm going to explain in more detail the story involving Weinberg's soft graviton theorem, which is the statement about the sort of leading singularity, so the leading pole. And as Alok explained, so here, just to be clear, so on this side, this is supposed to represent some scattering process between some set of particles in an out and in state. And here I've added an additional, or included the additional emission of a graviton. And in order to pick out the pole and frequency, well, I do this projection. So I multiply by frequency and take the limit, omega goes to 0. What one finds is that this is given by this same scattering amplitude between the particles that comprise this set of this in and out state. In this case, multiplied by this number, and it's known as the soft factor. And this is, if you remember from the previous talk, it takes this form. And so basically these are the momenta of the other particles in this in or out state. Here, as I mentioned on the previous slide, so I've taken the graviton momentum, and it will be helpful to parameterize it in terms of a frequency omega, and then a null vector, which I've chosen to be the first component to be 1, and the second, the remaining to be sort of a unit vector, which you can think of as specifying a point on the two-dimensional sphere. So now I'm going to review or sketch how one arrives at this statement just from the language of Feynman diagrams. So let's consider the S matrix element for emitting an outgoing graviton of momentum q, and find the leading order term as we take this q to 0. And so if we think of a scattering process involving in particles, and we want to then relate it to a scattering process in which we emit an additional graviton, well, then Feynman rules tell us that sort of all the classes of diagrams that the entire class of diagrams that will contribute are the original class of diagrams where we attach the graviton, this external graviton, in all possible ways. And so roughly speaking, you can then divide the classes of diagrams into 2 categories. There's the ones where this graviton is emitted from an external line, and then ones where the graviton is emitted from an internal line. So let's first think about the contribution when a graviton is emitted from an external line. And we can relate it to the scattering amplitude where there was no graviton emission. And the way we do that is we notice that essentially this entire diagram is related to the diagram without a graviton emission, if we just sort of break this line here. And so the difference between the two is the vertex between this particle and the graviton, and then an additional factor of the propagator associated to this particle. So the particle of type K. And then if we look at just this diagram here, well, this is just the scattering amplitude for between these in particles, except that now the momentum of the kth particle has been shifted to include this additional q. So I haven't taken q to 0 yet. I'm just looking at what the contribution of this diagram is for finite q. Okay, but now let's see what happens when we take q to 0 and just keep the leading order terms. Well, the first thing is, well, first let's write down what this vertex is. And essentially, okay, this vertex is coming from the coupling of a graviton to the stress energy of that stress energy tensor of that particle, which, for a scalar is two derivatives of the field. And so it comes with two powers of momentum. That's this. And then it also contracts with the polarization for the graviton, which is this. And because the graviton is on shells, so it's an external graviton, it's usually the polarization is taken to be orthogonal to that momentum. So roughly speaking, the only momenta in the game are pk and q, the momentum of the graviton. So actually, this is the only thing you can really write down. So that's the vertex. And then this is propagator for a scalar. And now we see that if we expand in small q, well, again, because this external particle is also on shell, that means that pk squared is minus mk squared. And so what that means is that to leading order, this propagator contains a pole in Q. So the p squared term cancels the m squared term, and the leading order term is a pole in Q. So thus, we found that the contribution from this set of diagrams to leading order in Q involves a pole in Q, and actually sort of gives us the saw factor that I had written down before.
So a quick question. So if here you assume that the particle is scalar, and if this are spinning particles, and this vertex is a 3-point amplitude, right?
Yeah.
And this 3-point amplitude for spinning particles, they can have more than one structure. If you have, say, non-minimal coupling for the gravitons, so all these guys are suppressed, right? Compared to...
They're suppressed because if you think about it, right, you're expanding to leading order and momentum.
Yeah.
And those other structures are going to contain more powers of momentum and be suppressed. Those structures do play a role in the subleading terms. And it turns out, but again, because of the momentum, count powers of momentum, there's a finite number of terms that correct them, and they're all written down in them.
Okay, so when is the first time that they enter?
Good. So, right, so, oops. Sorry. Right, so for corrections, we have for engaged theory, it's at subleading, which is order omega to the 0, and in gravity, it's at sub-subleading. And this is at order omega. And so an example of one engaged theory would be something like H mu nu, or let me not write indices, but sorry. The one engaged theory is something like an HF squared term, and a one in gravity would be something like an RF squared term. Right. Okay. So now we can consider the net contribution from sort of all of this entire class of diagrams where gravitons are emitted just from gravitons are emitted from an external line. And so to do that, we just sum over all the external lines, and we get what I had told you was actually the entire contribution at leading order in small q of the expansion of an amplitude for the emission of a graviton. And as I said previously, sort of the important point to notice is that leading order at small q involves a simple pole in the momentum of the graviton q. And so finally, I said that there's also this sort of second class of diagrams where a graviton is emitted from an internal line. And so let's suppose that this internal line carries some momentum L. So you might have, L and L plus Q. And so then, the contribution essentially from this sort of emission. So this is one of the propagators. This is the vertex by the same argument I gave previously. Again, the only other momentum in the game is Q. So actually, this is the only type of contraction you can have. But now, Q also runs through, let's say, this other internal momentum. But the important point to notice here is that if we want to find the leading order behavior, well, even though, of course, we're integrating over this internal momentum L, we can expand in Q. And here, what we find is that at leading order, well, L is no longer on shell. And so the leading order part is Q independent. And so there is no pole in the Q goes to zero limit. So that's just to say that the second class of diagrams don't contribute to the leading order behavior at small q. Okay, so that is how you derive this statement that the leading order behavior of a scattering amplitude in which you emit a soft graviton has a pole in the frequency of that soft graviton, and the residue of that pole is the soft factor.
Yes, there is some funny doubling. I'm wondering if it's if we can fix it by muting someone. Or...
Oh, yeah. Multiplied by the scattering amplitude without that graviton. And so sort of through this longer argument by just looking at properties of Feynman diagrams, I argued that there is this universal behavior of scattering amplitudes for the emission of a soft graviton in an expansion about its energy. And sort of the physical reason why you think this should be true is that this low energy graviton is probing long distance properties of the scattering process. And so in particular, you notice that this thing doesn't even know about, for example, the spin of the particles. Whereas if you remember, the subleading correction that Alok wrote down, well, that knew about angular momentum. So we would know something about a little bit more detail of the scattering process. And so this is the statement that it's universal and is independent of the precise theory. It doesn't know about things like what type of spin of particles are in your theory, and it's also universal in the sense that you get the same contribution for every external particle. But never. So what I'd like to now argue is that actually this universality can be understood as resulting from a symmetry. And so, the rough picture of why you might think this is true is because this soft graviton theorem is telling you an exact relationship among scattering amplitudes. And if you think about how what symmetries in the language of scattering amplitudes are, they're also exact relationships among scattering amplitudes. So in particular, if you have, for example, a continuous symmetry or a symmetry that's generated where the finite transformation is implemented by some operator U, then what a symmetry is it tells you that, if you transform the in and the out state, that's equal to the scattering amplitude without transforming them. And if you write it in terms of a generator Q, well, then this implies that the charge commutes with the S matrix. And so our goal now will be to turn this statement, which I derived for you from Feynman diagrams, into a statement like this.
So can I ask one quick question?
Yeah.
So the leading soft factor you can understand from gauge invariance, which is, well, some fake symmetry in some sense. So how should I think about it? Like now you're going to tell that there's like some actual symmetry that's related to the soft factor and not just ordinary gauge invariance? So what's like,
Good,
how do you square the two facts?
good. So this is I'm going to allude to a statement that Alok also mentioned, which is that if you have a gauge symmetry, and you can, so if you have a gauge redundancy, you can write down a charge that generates that redundancy. But of course, when you act with that charge on a state that's physical, it should annihilate the state. This is to say that the finite transformation should preserve the state, right? Redundancies take you from the same state to the same state. And these charges, we'll see, do not annihilate the physical states generically. Is that helpful?
Maybe I'll ask the question later if it's still unclear, like once you're.
Okay, maybe I should also say, as Alok described, the symmetries that are associated to this the symmetries that are associated to Weinberg's soft graviton theorem are a set of diffeomorphisms, but they act non-trivially on the physical data. And so in quantum language, it's the statement that they're not annihilating the state, that they change it from one state to a different physical state. Okay, so now I'm going to give a sort of formal argument for how you can turn soft theorems, which you can think of as basically exact relationships between scattering amplitudes with a soft particle and scattering amplitudes without that soft particle, into statements of invariance of the S matrix under infinite dimensional symmetries. And sort of this I'm going to try and give in a more sort of formal, more formal statement, so that you can sort of generally see how the logic applies to also the sub-leading cases. Okay, so the argument is as follows. So we would begin with this soft graviton theorem. And the first thing we can do is let's focus on this side. Now, since there's this number, since this side is given by a sum over a bunch of numbers, and there's one for each particle in this in or out state, we can regard the soft factor associated to each particle in the in or out state as being the eigenvalue of some operator, which I'm going to call QH, or for Q hard, that is implementing some transformation delta on this single particle state. So just to remind you of the notation, so I'm considering a process in which there is a soft graviton that is emitted that has energy Q and is propagating in the direction x hat. And so this soft factor, since it depends on Q hat, where Q hat is this unit vector, it knows about the direction that the graviton is propagating. So that's just to say that now I can write this entire right-hand side as the net transformation of the asymptotic state, of the asymptotic state, which is comprised of single particle states, under a transformation that is generated by QH and depends on the direction in which the graviton is propagating. Now, as I said, if there's a symmetry of the S matrix, well, symmetry of the S matrix tells you that there's a charge that commutes with the S matrix. And since now this right-hand side can be written as this commutator of the S matrix with a charge, this is telling us that the S matrix is only invariant under this transformation, delta theta phi, provided that we add a soft particle. So this transformation of the single particle states is not a symmetry of the S matrix. We also need to add a soft particle. That's what the soft theorem tells us. sort of with this symmetry interpretation in mind, what we can do is we can construct a second operator whose job in life adds soft particles to the asymptotic state. So this is something like this, and these are creation and annihilation operators of graviton modes. And with that, now you can write the left-hand side in a similar way as the right-hand side as being the commutator of this charge, QS, which adds the soft particles to the asymptotic state. And then if you rearrange the soft theorem by bringing, rewriting this in terms of a commutator with S and bringing both to one side, then you find that the soft theorem is simply the statement that there is a charge that commutes with the S matrix, and that charge is just given by the sum of the hard charge and the soft charge, where the hard charge acts on the single particle states, and the single particle states are eigenstates of this hard charge, with eigenvalue being the soft factor, and the soft charge adds particles to the state. And now, since I could construct these charges for every direction in which the soft graviton can propagate, I find that there are actually an infinite number of symmetries. There's a symmetry labeled by every point on the sphere, the point associated to the direction of the propagation of the soft graviton. And so by this argument, you can always interpret a soft theorem as a statement of invariance of the S matrix under an infinite dimensional symmetry. Okay, but the next thing we want to do is we want to see that these infinite dimensional symmetries were actually, in fact, the supertranslations that Alok had introduced in the previous talk. And so in order to do that, it's nice to instead parameterize, instead of parameterizing these symmetry transformations by the point that the graviton was, towards which the graviton was propagating, we want to parameterize them by functions on the sphere. And so there's a sort of preferred or nice way to do that. And the idea is that you can actually identify the soft factor. So now if we consider the case where the other particles participating in the scattering process are also massless particles, well, then we can parameterize them in terms of their energies and points on the sphere as well. And then what you find is you can show that this Green's function is in fact, that the soft factor is in fact a Green's function on the sphere. So that is to say that there exists some differential operator, which when you act on the soft factor, localizes to a delta function that has support when the momentum of the soft graviton aligns with the momentum of the massless particle. And so sometime in this, it's nice to work to parameterize the points on the sphere with stereographic coordinates. And so, this is a picture depicting how you actually get these stereographic coordinates. This is actually the formula for them. And then, just to understand sort of what this differential operator is, if you write the soft factor with this parameterization, it takes some form like this. And then you can see that actually this differential operator is some second order differential with respect to z bar, which was associated to the graviton, the direction in which the graviton was propagating. Okay, so now we know the soft factor, if in a scattering process involving massless particles, is a Green's function. So why is that nice? Well, we can use this fact now to construct charges that have a local action. I'll explain what that means on massless particles. So in particular, we take our old charge, which was parameterized by the point in which the graviton was propagating. We act with this derivative operator, and we integrate it against an arbitrary function f. So now, with this new set of charges, if we want to deduce their action on massless particles, well, so again, the hard charge is then given by a similar formula where you take the old hard charge, act with the derivative operator, and integrate it against this function. And since the old hard charge gave you the soft factor, and then upon acting with this derivative operator, the soft factor turns into a delta function. And then when you integrate against this function f, then you find that the transformation that this set of charges implements on single particle states returns the energy and this function f evaluated at the point on the sphere associated to the direction in which this massless particle is propagating. So this is the sense in which these charges act locally on massless particles. Okay, so, but now that we've identified this sort of another way of phrasing the symmetry implied by the soft theorems, we can now determine sort of more physically what they mean. And so here, I've just rewritten this new way of writing the charges, and again, their action on single particle massless states. And the point is to notice that when, okay, f is a constant, then the transformation of single particle states under this particular symmetry just returns their energy. But we know that a transformation of a momentum eigenstate that returns its energy is just an ordinary time translation. So we can identify the charge with f equals to 1 as generating time translations, ordinary time translations. But of course, we have not just this constant f, we have, an arbitrary function of f. And, and as I said, sort of the transformation that is generated by an arbitrary function of f is now giving you the energy weighted over the sphere by this function f. And so therefore, this charge is generating a translation that's weighted at each angle by this function f. And since f is an arbitrary function, this means that there is an independent translation symmetry at every angle. And this was what was previously described as supertranslations. And moreover, since f is an arbitrary function, we can see that the entire class of hard charges, which for every function f, are characterizing the local energy flux at every angle. And so I'm going to explain both of these statements in more detail now. So, from the last slide, it sort of maybe seems obvious, but if you think about it a little bit harder, you might get a little confused as to why transformations that are acting at every angle in momentum space are also acting every angle in position space, which is the symmetry transformations that Alok had introduced in the last lecture. And so the precise way to understand why this is true follows from a saddle point approximation argument. And so the basic idea is if you consider a plane wave for a massless particle, and you write the coordinates, the x coordinates, in terms of a retarded time and a radius and some unit 3 vector specifying a point on the sphere, well, simply rewriting it, it takes this form. But then you notice as you take the r to infinity limit, so in other words, you look at the behavior of a massless wave function as you approach null infinity, you see that this part here fluctuates wildly unless x hat dot x hat k is 1. So that is to say that the wave function for a massless particle localizes at null infinity in the direction that the momentum is pointing. And so using this fact, let's consider the expansion of, so this is the expansion of a massless scalar field in plane wave modes. And then what this means is that if we use a saddle point approximation, well, you find at leading order, this mode expansion falls off like 1 over r, and the leading order piece, so basically the point in position space aligns with the direction that the momentum is propagating. And so the only sort of non-local thing between momentum and position space is between frequency and time. And so moreover, if you consider then a super translation of this radiative data, well, as Alok had written, the supertranslation is basically, you can think of it as roughly this function f and a time derivative, retarded time derivative of the leading order data, and plugging in this expression here, you see that the action of a supertranslation on something in momentum space is exactly reproducing the action that we derive from the soft theorem upon rewriting the charges in terms of a local function f. So this is why Weinberg's soft graviton theorem is actually implying, or the symmetries implied by Weinberg's soft graviton theorem are equivalent to the supertranslations. And this is this is just reviewing sort of what Alok has said, is that okay, these symmetries could have been derived, were derived by Bondi, Vandenberg, Metzner, and Sachs back in the 60s from the asymptotic symmetry analysis, where they were looking for the allowed diffeomorphisms which preserve the boundary conditions quotiented by the trivial diffeomorphisms which acted on base space variables. And these were the sort of fall-off conditions they were taking. And yeah, these are the Bondi coordinates. And this was the result that they found. So again, this was the transformation that I used a couple slides ago. Okay, and so now I'm going to explain a little bit more carefully this idea that QH was characterizing the local energy flux at every angle. And that is just to say that now that we have this result from the saddle point approximation, that things that are local in angles in momentum space are also local in position space, we can actually just write down an operator expression that for this hard charge. And so in particular, and also now you can see sort of this is the quantum analog of what Alok had presented in the previous lecture. And so that's just to say that the expression for the hard charge is that it is the UU component of the stress energy tensor integrated against this function, arbitrary function f. And really it's sort of the leading order behavior of the UU component of the energy tensor. And just to verify that this sort of makes sense with everything we've said, so you can use canonical commutation relations. So for example, for scalar fields at null infinity, they obey some canonical commutation relation like this. And you can check that in position space, if you act with this hard charge on a scalar field, well, essentially one factor of this du phi contracts with this. And so we get, f du phi. And this is what we said was the supertranslation of this radiative data. And likewise in momentum space, you again use this relationship that now the only difference between momentum and position space is really a Fourier transform with respect to retarded time. And so this du gets replaced with a factor of energy, which was what we had argued from the soft theorem was the symmetry transformation of massless particles. But now, since this is the sort of operator expression for the hard charge, this is the sense in which TUU is telling you about is an energy density. So this is the sense in which QH is characterizing local energy flux at every angle. And again, because f is an arbitrary function, right? And you have a conservation law for every f, you can vary this expression with respect to f and therefore deduce that it's really local energy flux at every angle.
Monica, one question.
Yeah.
So in your argument, you showed us that you can construct these charges which commute with the S matrix, but the argument used Feynman diagrams, right? So it was perturbative. How would you? But I guess we believe that this is true non-perturbatively. right? That discharges commute was a full non-perturbative S matrix.
Well, maybe what I said is that I derived the soft theorem from a Feynman diagrammatic argument, but then the argument I used to actually go from a soft theorem to say that there are charges that commute with the S matrix was just a total rewriting. It's formal. It didn't rely on Feynman diagrams or anything. So long as you believe the soft theorem.
Right. So I'm trying to. So I guess one way you can think the soft theorem is a consequence of a symmetry, right? So you first say that there is a symmetry, and then you derive a soft theorem. But now you're saying you sort of start from soft theorem, and then you're saying that if we believe soft theorem non-perturbative, then there is a non-perturbative. So do we have an argument that the soft theorem is true non-perturbatively? Or I don't know what would be the
not that I know of, but I don't really know why it wouldn't be. I don't have a good argument.
Okay, thanks.
May I ask a question, Monica? You took a convention in which all particles are incoming or outgoing, right?
No, I didn't mean to. I meant there's an extra.
Otherwise, there are signs in your formula.
Yeah, so I meant, like.
No, well, the reason I'm asking, I mean, this is a triviality. The reason I'm asking is that Unlock distinguished, made his argument based on Sky plus and Sky minus, past, now, and past, future, infinity, whereas you seem to have only one of them. You always have U, you never see a V in your formula and so on. I guess this is just to simplify notation.
Yeah, it's just a simplified notation. Another way of saying it is that actually, BMS understood these symmetries as acting on a phase space which was defined either at past null infinity or future null infinity. And there's this, the sense in which they are symmetries of the S matrix, you have to tell me, what symmetry I implement on past null infinity, what symmetry is associated at future null infinity. And
but I thought your operator act also on the energetic particles assumed to be massless, or did I understand?
Yeah, so the energetic particles thus far I've talked about are massless. But
okay, that's not so nice, right? That you have to restrict to that case.
I'm about to get to
it.
This is massive. We're now going to move away from that. Yeah.
Okay.
Good. But let me just say that in some sense, you could have also have started from the soft theorem and use that to deduce which symmetries were actually the symmetries of the scattering problem, which require you to tell me, what symmetry at past null infinity is associated to what symmetry transformation at future null infinity. So the soft theorem actually knows about this antipodal matching condition and that antipodal matching condition could have been derived from the soft theorem.
Okay.
Right. Okay. So, but good. We don't want to just talk about scattering processes with massive particles. We'd also like to talk about scattering processes with massive particles. And so let's try and generalize that story. And the first thing to do is sort of remember, what so far we've said that relied on the fact that the other particles in the scattering process were massless. And so the key point that we've used so far is that actually, if these hard particles are massless, well, then the soft factor is this Green's function on the sphere. And that was nice because then we found that this hard charge was really, characterizing local energy flux through null infinity. Now, of course, as Alok already explained, massive particles and momentum eigenstates don't reach null infinity. And also, you can't, you wouldn't really expect the soft factor for massive particles to obey some sort of relationship like this, simply because there's no canonical way to associate massive momentum to points on the sphere like we could for massless momentum. And the easiest way to see this is to note for a massive particle, you can always put it in its rest frame. So it points in no direction. Its momentum points in no direction. But on the other hand, so the first formal argument I gave, where you started from the soft theorem and found that it implied infinite dimensional symmetries, well, this argument applied regardless of whether the particles were massive or massless. And so in particular, when we were parametrizing these charges by the point that the soft graviton was propagating, well, they implemented formally this symmetry transformation, and any single particle state was an eigenstate of the symmetry transformation, with the eigenvalue being the soft factor. And so really what we want to ask is, what is the transformation of massive particles under the symmetry? So this is just to say, we know what the transformation of massive particles under the symmetry that's generated by the charge when we were parameterizing it in terms of the direction that the soft graviton was propagating. But what we want to know is what the transformation of the massive particles is when we parameterize this symmetry instead by this function f. And that was, how we were sort of figuring out physically what the symmetry transformations were. And okay, so to answer that question, we just need to recall the relationship between the two different ways of writing the symmetry transformations. And simply that one is built out of the other. So that was, you take the symmetry, the charges which are parameterized by the direction that the soft graviton is propagating, you act with this derivative operator and you integrate it against a function on the sphere. Now, for massless particles, this derivative operator was localizing the soft factor, but if we just follow our nose and see what happens for massive particles, well, then, formally, we know that the symmetry transformation of massive particles then is, so we plug in, so it's generated by this charge, which is related to the other charge by this formula. This hard charge returns the eigenvalue of the soft factor. So formally, this is what the transformation of a massive particle is. Okay, but we'd like to do a little bit better and understand, why it takes this form and what that means. And so to understand that, the key point is to note that, of course, while massless particles are naturally associated to points on a sphere, the momentum of massive particles are naturally associated to points on the 3D hyperboloid. And so that is just to say that, the massive on-shell condition, right, is p squared is minus mk squared. And what that means is that you can write a massive momentum in terms of, you can parameterize it by sort of the overall mass, and then a point on the 3D hyperboloid. And this is just some parameterization where rho happens to be the radial coordinate and z bar the angular coordinates. And so Alok had introduced this in the previous talk, but likewise, you can parameterize points that are in the interior of the light cone emanating from the origin. So in other words, these points in Minkowski space. You can also parameterize them in terms of an overall, so a coordinate tau, and then again, points on the 3D hyperboloid. And by a similar saddle point approximation, so in this case, so previously we took this r to infinity and saw that massless particles localized to the point on the sphere towards which their momentum is directed. Here, if you take tau to infinity, then you learn that massive particles localize to the point on the 3D hyperboloid towards which their momentum is directed. So this is just to say that if you have a massless particle with some momentum, massive particles with some momentum like this, and or massive plane wave, and you rewrite it in terms of these points on a 3D hyperboloid, then you'll find that the wave function, the plane wave for this massive particle, rho k will localize to the point rho, zk and zk to z and z bar. And the reason why that's nice is that allows us actually to simplify this expression and understand what it is. And so what you do is, if you actually calculate this thing, what you find is that it is nothing more than a bulked boundary propagator on Euclidean ADS3 from the point associated to that massive momentum to a point on the sphere. And so what you learn is that actually the transformation of massive particles by these symmetries parameterized by functions are given by that function, the original function. So all the symmetries are parameterized by functions on the sphere, but in order to act on the massive particle, you need to propagate it from that point on the sphere to the point on the hyperboloid associated to the direction of that massive momentum. And what was shown in this paper is that really this is the extension of this gauge parameter f from null infinity to time-like infinity under the de gauge condition. So that's how you can understand the symmetry transformation of massive particles. Okay, so let me recap sort of what I've said so far and give the direction sort of for the rest of the lecture, and then probably it's a good time for a break. I introduced the soft theorems as basically the quantum theoretic characterization of the universality of gravitational radiation in the infrared. And so this is supposed to complement the picture that Alok, or the analysis that Alok presented, where you can study just classical radiation and find, again, some universal properties of gravitational radiation in the infrared. And by showing, but then one can take these soft theorems and show that they're equivalent to ward identities for infinite dimensional symmetry. And what you learn from that is that the universal behavior in the infrared was actually equivalent to universal behavior due to symmetry. And so there was a sort of formal argument for why this was true. But at the end of the day, we wanted to be able to identify these symmetries with something that was previously known. And in order to do that, we spent a bunch of time studying the action of the hard charge, which on single particle states. And so single particle states were supposed to be eigenstates of these hard charges. And by rewriting it in certain ways, we learned that the symmetry implied by Weinberg's soft graviton theorem, or we could identify that the symmetry implied by Weinberg's soft graviton theorem as being the supertranslations discovered by BMS. And so apart from deriving the soft theorem and showing that those soft theorems were equivalent to ward identities, we essentially ignored the role of the soft charge. And so the next part of the talk, we're going to revisit this soft charge. And so in particular, we're going to try and understand better why we need this soft charge, and in what sense does it implement a symmetry transformation? So in particular, what transformation is it implementing and what is it acting on? So that will be, the next part of the talk. So maybe questions and 10-minute break.
Questions and maybe 5-minute break.
whatever it was, yeah.
Okay, so don't think there are immediate questions. We will have time for discussion, so let's take a 5-minute break then. And we will restart at 45 past 5 Florence time.
Sorry, Monica, can I ask you one more question?
Yes.
I mean, it's similar to the, it's still related to what I asked before. So like, there's just a statement that the universality of the soft theorem is due to this infinite limit or this new symmetry. I mean, the leading soft theorem is just completely dictated by gauge invariance, right? So, I mean, the universality basically is, well, it's a consequence of that. I mean, you could, whatever you take, like, I mean, you can either say, it's a consequence of both in some sense, right? Like, it's just like from linearized gauge invariance, just demanding that, like, if I replace the graviton, the on-shell graviton polarization vector by its momentum, it has to vanish and stuff in the soft limit. I can derive the soft factor, right? So in that sense, and as you said, like from the soft theorem point of view, whether you have massless or massive particles in the scattering process, it just doesn't matter. Whereas like in this construction with these charges, like there is a distinct, like, I mean, you have to distinguish these two cases, whether you have like massless particles or massive particles. So it's just, I mean, the construction is slightly different, right? I mean, as you showed. So, I mean, yeah, I mean, I think it's just like something, it's just a moral question, like whether you should, yeah. So I guess there's just.
Maybe what is like, right, so actually good. So what you're saying also actually answers the question that Sasha answered earlier, which is really, yeah, this isn't a non-perturbative statement, right? Like, because it follows from, there's an argument, a scattering, you know, quantum field theoretic argument from gauge invariance, which you're correct, right? What is obscured in that, you know, derivation, right, is the fact that these symmetries are physical symmetries and that they're not to be viewed as gauge redundancies. And that's a little, yeah. Yeah,
that's completely hard to see because, yeah, I mean, because I just view it as like exactly like the word, I am just using exactly the word identity of the gauge symmetry to derive this theorem. And I don't see that there's like anything non-trivial asymptotically going on from that point of view, I guess. So that's the point that these BMS charges clarify.
Yeah.
I don't know if I can add maybe one reflection on this related to Enrico's comment. So I guess to some extent it's important to distinguish between the factorization fact and the consequences that you need to have when you impose that the amplitude vanish when you replace epsilon with the momentum, right? So somehow BMS allows you to really rederive the factorization without using the polology argument. And then on top of that, if you reimpose somehow gauge invariance, this leads to consequences like the conservation of electric charge and the equivalence principle. But this is somehow in this procedure, gauge invariance comes in as a step later somehow, right?
Yeah. Yes. Yeah.
Okay, maybe we can restart.
Okay. Okay, so as I mentioned right before the break, the second part of the talk will focus on, you know, what the role of the soft charge is. And so the first thing I want to say is, you know, why did we need that contribution? You know, in what sense are these symmetries, if we hadn't included that contribution? Because, you know, if you think about, you maybe naively think about how supertranslations act, you never saw that part. We could sort of deduce that these were supertranslations without ever looking at the soft factor. So to do this, let's look at the soft charge, or sorry, without ever looking at the soft charge. So let's look at the soft charge we never looked at it parametrized by this function f. We only ever looked at it parametrized by the direction in which the soft gravitons were propagating. Okay, so again, but the form of the hard charge fixes the form of the soft charge, so it's given by acting with this differential operator and integrating against a function on the sphere. Now, we can integrate this differential operator by parts and instead have it act on this function. And the important point to notice is that actually there are some choices of f, which I'm calling f hat, for which are annihilated by this differential operator. And what it means is that, okay, that means that for those choices of f, so that set of charges, the soft charge vanishes, and we had a symmetry without needing this soft charge. So which ones are those? Well, in the case of supertranslations, what one can show is that actually the set of functions for which the soft charge vanishes are the first 4 spherical harmonics. So the L equals 0, 1, and then the 3 L equals 1 ones. And as Alok had already told us, actually, those are the 4 ordinary translations. And so this is good. What we've just found is that when there are 4 of this infinitely many set of charges parameterized by f, we could think of decomposing f into spherical harmonics, and then there are 4 of them for which one doesn't need a soft contribution, and these symmetry transformations are the ordinary translations, which we think that scattering amplitudes are symmetries of scattering amplitudes. And so the important point to take away is that there are sort of finitely many symmetry transformations which preserve the number of particles in the scattering amplitude, but if we want this infinite dimensional enhancement, then we need to include symmetry transformations in which they act on a state by adding soft particles. And so the generic case for generic f, in the generic case, this contribution doesn't vanish, and those are where we find the infinite number of symmetry transformations. Okay, so another thing to say about the soft charge is, like for the hard charge, we can identify an operator expression for this field. And so the basic way to do that is just to use properties of the Fourier transform. So I'd already showed you that for massless wave packets, they localize to the point on the sphere, so all you really need to do is Fourier transform with respect to retarded time. So really this, sorry, t here is the u from before. And so we can identify the contribution from the soft charge as involving, the 0 frequency limit of the radiative gravitational field. And, the connection with memory is to notice that if we take omega to 0, then we can actually interpret this contribution from the soft charge as encoding or telling us as equivalent to a permanent net shift in the asymptotic metric. And another way of saying this is the Weinberg's leading soft graviton theorem is telling us about a pole in frequency space. And if you Fourier transform that, you find a step function in time. And so that's this permanent shift. Okay, so that's the classical statement. And so, one version of the classical statement is, I've shown from this, shown in this clip from this paper by Roginski and Thorne, which is basically if you consider the scattering of a bunch of bodies with momentum capital PA, well, then they induce the following change, permanent shift in the asymptotic metric. And this is something you can also understand in the language of scattering amplitudes. And that is that, so if you start with the soft theorem, then So I just explained on the previous slide that this zero frequency component of the radiative gravitational field is equivalent to the operator for the permanent shift in the asymptotic metric. And so if you divide both sides by this scattering amplitude, then you can see that one way of interpreting the soft theorem is it's telling you the expectation value for the permanent shift in the asymptotic metric in the background of a scattering process. And in the background of a scattering process of point particles, the expectation value for this permanent shift is the soft factor. Okay. So with those pieces of information, now we're going to sort of turn to this question of in what sense does this soft charge implement an infinitesimal symmetry transformation? And to answer this question, let us notice the following. So let's consider the action of this soft charge on a vacuum state. So in other words, a state of zero energy. Now, the soft charge was comprised of zero energy gravitons. And so if you act with the soft charge on a state of zero energy, you get a state of zero energy. So being totally agnostic, we know that at least it maps some vacuum to a vacuum. It could be the same vacuum. And so from that, we learn that this soft charge is implementing a symmetry transformation on vacuum. Okay, so with that piece of information, let's revisit the Ward identity. And let's consider, let's label our vacuum states by their eigenvalue under this soft charge. So let's choose to study this class of vacuum states. And so that's just to say, we'll call them we'll give label them by alpha, and alpha is their eigenvalue under the soft charge. And now let's consider scattering states, which we make by acting with creation operators of finite energy particles atop this vacuum. And now these finite energy particles will not affect the action of the soft charge. So generically, the action of this soft charge on these states will still be the same as it was as it was on just the vacuum itself. Okay, so now let's consider the Ward identity between the following set of scattering states. So we want to consider the Ward identity where we have some set of, so out is to denote some set of finite energy particles, and they're put atop some vacuum, which I'm labeling alpha out. And our in state is some set of incoming particles atop our vacuum alpha n. So, okay, this is the action of the hard charge. We already knew how to do that. That acts non-trivially on finite energy particles, and that we found was giving us this soft factor. And now we know how to evaluate this right-hand side, which is that we're working, these states are also eigenstates of the soft charge, and their eigenvalues are alpha in or alpha out. Okay, but now equating these two and bringing both to one side, we find that the Ward identity is equivalent to this statement, that the net soft factor plus the eigenvalue, the eigenvalue of the out vacuum minus the eigenvalue of the in vacuum multiplied by the scattering amplitude is 0. Okay, well, so I've rewritten this equation, and this equation has two solutions. Either that the scattering amplitudes are 0, or that the eigenvalues satisfy this constraint. And so what we've learned from this is that a degeneracy of vacuum states is necessary to have non-trivial scatter. So in other words, if we want the S matrix elements to be non-zero, it must be the case that alpha in and alpha out are not the same. Or in other words, the vacuum of the in and the out state are not the same. And in particular, that their difference is given by, the difference in their eigenvalues is given by the soft factor. And so that is to say that if we were assuming a unique vacuum, then we would expect then these two eigenvalues would be the same. And we conclude that the S matrix elements vanish. And sort of the selection rule for having non-trivial S matrix elements is that the difference in the eigenvalues is the soft factor. So the next thing to ask is, do the standard scattering states account for this degeneracy? And to answer this question, we're going to take a slight detour, and I'm going to recall for you the story of infrared divergences in scattering amplitudes. And so in particular, the infrared divergences that are due to the exchanges of soft virtual gravitons. So let's consider the contribution from a virtual graviton that's exchanged between external lines. So if we want to sort of approximate the contribution to a loop integral from, so now Q is an internal momentum. So to approximate the contribution from small q, we can Taylor expand the integrand about small q. And sort of by a similar argument as what I described previously, what you find to leading order by Taylor expanding sort of this contribution about small q is this thing here. So this is what you might have recognized as, so this is the soft factor, but it's, expanding the vertex operator and this momentum about small q. This is just the graviton propagator. And then this is the expansion of, this vertex and propagator about small q. And to leading order, we see that it factorizes. So it's this contribution, and then it's this q independent piece, which is basically this same diagram without the additional exchange. And then there's, of course, subleading corrections. And the point is that if you count powers of q, so we have 4 here and then 4 in the denominator, that means that this loop integrand contains a logarithmic divergence from the q equals 0 region, and that this logarithmic divergence factorizes. So you might similarly ask, okay, well, what happens if you have multiple soft exchanges, such as those between, different lines, between 2 of the same lines or different lines like that? And sort of the way to understand that story is to consider what happens when you have multiple soft emissions from a single line. And there, so here I've already expanded in small q1 and q2. So this factor is sort of the contribution from this vertex and this propagator, and this factor is the contribution from this vertex and this propagator. And likewise, this factor is a contribution from this vertex and this propagator, and this contribution from this vertex and this propagator. And the point is that if you exchange over the different orders of emitting soft gravitons, then you find that actually the net contribution is just this factorized product. And so if you apply this to the multiple exchanges between external legs, then you deduce that actually the contributions from multiple exchanges are multiplicative at leading order. And moreover, an efficient way to sum all these exchanges is to note that if you want to reproduce this sort of multiplicative factor, well, actually, a Wilson line operator for for gravitons just reproduces the Feynman rule for basically multiple soft exchanges, summing over all possible orderings. And the way to see this is just to start with a Wilson line operator and plug in a mode expansion, and essentially that allows you to you can form the tau integral, and that acts on this tau integral. So tau basically appears in this exponential, and once you perform the integral, you get this, you get the pole factor, and then this is just the soft factor. And so that is just to say that if you consider the S matrix element, and you want to find all these sort of leading IR divergences, well, what you find is that the S matrix factorizes into a piece that contains these leading IR divergences and a piece that is IR finite, where the piece that is containing these IR divergences can be written roughly as an expectation value of these Wilson line operators. And this is the sort of explicit expression. So essentially it's exponentiating so by summing over all possible exchanges, you exponentiate the sort of one exchange. And this was, roughly speaking, this is the result from one exchange that I had presented earlier. So this was the soft factor, the soft graviton propagator, and the other soft factor. And as I mentioned, since there are 4 powers of momentum in the numerator and 4 in the denominator, this object has an infrared divergence at small q. So I've cut it off with lambda IR. And then I put another cutoff, lambda, which you can think of as the soft hard separation scale in this factorization. And what Weinberg showed back in 1965 is that actually, okay, so if you perform this integral, you can rewrite it in some form. So this entire thing is proportional to a logarithm of lambda over lambda IR. And that factor proportionality, I'm calling A. And the point is that A is positive. So as you take the cutoff to 0, then you find that this infrared divergent piece vanishes. So this is just to say that the virtual IR divergences that arise from the exchange of soft gravitons between external lines cause all exclusive scattering amplitudes to vanish. So now the question is, well, is this the same vanishing of scattering amplitudes that we found previously from symmetry arguments when the vacuum was taken to be unique? So to answer this question, let's consider how you might change the soft charge that's carried by the vacuum. So you can do this by constructing an operator, which I'm going to call W of alpha, that has the property that when you commute it with a soft charge, it gives you back that operator multiplied by this function alpha, by some function alpha. And then formally, you can see that, okay, now if I act with a soft charge on a vacuum with some value alpha naught, that's acted first on by this W alpha operator, well then, from this commutation relation, this object carries instead the eigenvalue alpha plus alpha naught. And so therefore, this operator does the job of changing the soft charge by an amount alpha. Okay, so to actually construct it, it's nice to write it instead in this form, where now I've included, so alpha again is just some eigenvalue and C is some field. And like I said, we're looking for an operator that obeys this commutation relation. And by writing this operator as an exponential, that means that we're looking for some operator C, which is basically symplectically paired with the soft charge. And since C is conjugate to the soft charge, it can naturally be interpreted as the Goldstone boson. And in particular, instead, if you were parameterizing it by functions f, then that's just telling you that the action Q S on C is IF, which is basically, which is then the symmetry transformation of C, and this is telling you that C actually shifts non-linearly under the symmetry, which is what we think of as how Goldstone bosons transform under a symmetry transformation. Okay, and so now to explicitly find an expression for this charge, we can first write down the sort of expression for a soft charge, and then it's easy to check that actually the sort of right expression for this Goldstone boson is something like this. And in particular, you don't need a unique expression. All you need is for this function. This is not, sorry, this I should have called a different function. There's no unique expression, but you need this F tilde to satisfy this boundary condition. And so the way to check this is, again, so C was supposed to be symplectically paired with QS. And now you can just use standard creation annihilation mode commutation relations to check that that's actually true. So this is the standard momentum space ones. And if you rewrite them in terms of omega and x hat, so you note that actually like this scales like 1 over p cubed multiplied by p. So that means this whole thing scales like 1 over p squared, which means that this is the correct statement, scales like 1 over energy squared. And so plugging this in, one of them is this limit omega goes to 0, and the other one is this integral. Plugging this in for this relationship here, then we see that this omega cancels that omega. We take the integral over this delta function, and we find f of 0, which we said needed to obey this condition. So this does actually construct for you the symplectic pair of this soft charge. And so putting everything together, this is just to say that actually we can change the value of the soft charge by applying this operator, which is an exponential of the Goldstone boson and has some explicit graviton construction. And therefore, in order to satisfy this constraint, let's assume that the vacuum was unique and change the out vacuum by this soft factor in order to satisfy this constraint by applying this operator with alpha set to be the soft factor of the out state. And so upon doing this, what you find is that if you take now this expression for this operator that changes the value of the soft factor, you put in the expression for the Goldstone boson in terms of gravitons, and also taking alpha to be given by the soft factor, and you simplify this whole thing. Well, what you find is this is exactly the Wilson line we had considered earlier, which was computing for you the IR divergences up to a sign. So that's why it's this dagger. And so this is just to say that the contribution now from soft virtual gravitons that are emitted and absorbed from external lines is precisely canceled by the emission or absorption of soft gravitons from this dressing. And so this you can then show implies that the amplitudes which satisfy the constraint are in fact infrared finite. So to summarize, this is to say that the fact that scattering amplitudes, or actually let me say, so summary of this section is that so the infrared divergences that set scattering amplitudes to 0 are a consequence of violating the constraint that's due to supertranslation symmetry. And so, and physically, the dressings that are needed to satisfy the constraints are representing the gravitational radiation that's emitted during non-trivial scattering. So in particular, you were starting with, for example, let's say a scattering process involving only hard particles. And what the symmetry constraint is telling you is that you at least need to add in the coherent states of gravitons that are capturing the soft radiation required by the symmetry constraints. And so what we've learned is that in the scattering process, the soft sector is, required by the supertranslation symmetry to agree with the classical result. So in other words, the classical waveform at low frequencies. Okay, I guess my time is up. So let me just say summary. So in the first part, we started with soft theorems for scattering amplitudes. And what those were is that was a universal behavior. We found that the universal behavior of low frequency radiation in the language of scattering amplitudes is captured by exact relationships among scattering amplitudes, which are known as soft theorems. Then there was a systematic way to rewrite soft theorems as Ward identities for infinite dimensional symmetries. And from that, we learned that this universal behavior in the infrared is actually equivalent to universal behavior due to symmetry. And by studying the action of the hard charge, we were able to identify the symmetries implied by the soft theorems as supertranslations, which are derived from an asymptotic symmetry analysis. And finally, in the last part, we wanted to understand better the role of the soft charge in the symmetry and in scattering amplitudes. And what we learned is that the soft charge was implementing a symmetry transformation on the vacuum, and that the infrared divergences, which set exclusive scattering amplitudes to 0, are a consequence of scattering states that violate the symmetry constraint. So that's the end of my talk.
Thank you very much, Monica. I'm sure everyone can join me in thanking you for this talk. And we now have time for a few questions. I guess then we will have a break and have more open discussion. So please, if you have questions, raise your hand and ask them. Maybe I can ask, because I don't see any hands yet, so maybe I can ask a quick question. So usually when we study the sort of the standard perturbative scattering amplitudes in momentum space, one powerful tool that people have been using a lot with dispersion relations, right? Now in D=4, if we want to do it for quantum gravity, we cannot do it because of infrared divergences. So amplitude is not well defined. So now we can use these dressed amplitudes that you told us about. Is it clear how to write dispersion relations for these objects? Namely, how unitarity, analyticity, things which are very clear in momentum space, what happens to them in the presence of these Wilson lines?
It's actually even, I think the difficulty is probably even more basic than that, in the sense that the clouds that you need to add, while the only part that is necessary to satisfy the symmetry constraint is sort of the zero frequency part, the general expression for these clouds involve gravitons that carry energy.
Yes.
So even things like, what the momentum is of what momentum is in the scattering amplitudes is complicated. And so if you want to write dispersion relations in which you work in Mandelstam invariance and you assume certain properties, I think even more basic questions need to be like, how are you supposed to parameterize these and before.
And you also had recently this paper on celestial amplitudes, and so does it work better there? So can one write dispersion relation using the celestial amplitudes? Or?
So there, it works a little better simply in that there's a preferred dressing, because essentially there's a preferred conformally covariant dressing. Dispersion relations, perhaps, but that's very unexplored at this moment,
Okay.
essentially because, yeah, the variables you talk about are not the same.
No.
So in particular, if you're studying, 4-point scattering amplitudes of, particles, so the statement is for particles in boost eigenstates, instead of the, S and T, so center mass energy and momentum transfer, well, momentum is no longer quantum number in this
Yes.
language, it's an operator. And so the numbers that you have are the conformal cross ratio, which is essentially the scattering angle. And then, so that's the ratio of S to T. That's something that still makes sense.
Mm-hmm.
And then, so if you have the ratio of S to T, something needs to replace the overall energy scale. And that turns out to be the sum of the boost weights of the states. But precisely, I have a paper where we explain some set of observations of what the energetic behavior is, but it's not clear, what the full set of.
Okay, thank you. Any more questions? Okay, Enrico, please.
Yeah, so this relation between IR divergences and this, this degeneracy. So if I go beyond 4 dimensions, for example, I go to 4 plus epsilon dimensions, or 5 dimensions, or whatever you want. So then, like, there are no the IR divergences are just gone. So, like, why is there so much focus in d equals 4 on the IR divergence? I mean, the IR divergence, as you showed in gravity, is kind of trivial, right? It just exponentiates out. I can either say I can make well-defined amplitudes by just taking the hard amplitude by just exactly stripping off the soft factor. But then also, so if I'm above d equals 4 dimensions, there's just no IR divergences. So what would you say that the problem is there? Like, I guess, like, is there still some degeneracy beyond d equals 4 that you need to take into account? Because now you can't argue with the IR divergence anymore.
Yeah, so I would agree that right. So there's several things to say. So first of all, if you do an analysis in higher dimensions at a classical level, and you ask sort of the classical version of this question, which is what are the classical vacuum configurations, which are these different degenerate vacua. So in 4 dimensions, it's telling you roughly about the connection on the sphere it's telling you about the connection on the sphere at null infinity. And in higher dimensions, it's some subleading effect, like bar subleading effect at null infinity. And so this also, so basically this is an open question, but like, depending on how people construct the charges, there's also a way in which you can construct charges at null infinity, which in higher dimensions, which can be shown to be equivalent to the soft theorem, but if you actually count powers of R, they vanish. And, this is likely related to the fact that, like you said, if you look for, there are no IR divergences in higher dimensions. So no, it's not clear how this story, it hasn't been worked out, or it's clear how the story generalizes to higher dimensions. But let's just say that there are other aspects of the story in higher dimensions which are also not as less clear than in 4 dimensions. So Yeah.
Any other questions? So maybe I can quickly follow up on Enrico's question. So for a lot in d equals 4, there was this log omega term, which was a little bit special that he mentioned. So did it play any role in your story, in this story with Wilson lines, this log of omega in the soft expansion? Somehow or it's...
So it is somewhat related in that if you actually look, okay, so again, I don't think this is like fully worked out. So that log omega term, first of all, maybe the first thing to say is that log omega is different from, is not the log divergence that I was talking about, simply because the log omega, you know, at the basic level, because log omega he's talking about, that's a logarithm in the momentum of the external particle of the committed graviton. And the one I'm talking about is the logarithm in the virtual.
Right. Yes.
That being said, you know, if you look at, you know, the saw factor, or sort of, you know, the coefficient that's next to this log omega, it has a more similar form as, and I think some of the terms are similar, if not the same, as the coefficient of the log of the infrared cutoff. And so, unlike, if you consider the scattering of just a bunch of particles, unlike the other saw factors, which sort of have one term per particle, these log terms have involve pairs of particles. And you should understand this because they're capturing, you know, the logarithmic, it's a logarithmic effect due to the fact that the particles are interacting at not long distances. So it's not just like a single particle, it's their pairwise, and their pairwise interaction is a similar form as the one that appears in the infrared divergence.
Okay.
Sorry, put differently, I mean, you described how these symmetries imply the leading soft theorem, but I didn't understand if you have also derivation of the subleading terms, say not about the 1 over omega, including the log, but in general, can you go beyond the leading soft term?
Yes. So I think the story is most clear for the subleading, so order 1, and subleading in gravity. So in gravity, if you ignore this subtlety with log contributions, there's an order 1 piece.
Right.
There's an order 1 piece and an order omega piece, which are universal but less so. And they can be interpreted, again, but they can similarly be interpreted as word identities of symmetries. The first subleading one, so the order 1 piece, is the quantum statement of the enhancement of the Lorentz group to like the Virasoro that Alok had introduced. Yeah. And then the subleading one is something new and simply different, and sort of, you know, formally you can figure out what the action on you know, single particle states is, because it's whatever that subleading saw factor is, which involves angular momentum and of angular momentum and momentum of particles. But right, yeah.
Okay, so you have to go into those enlargement of the symmetry in order to get the subleading terms. Super translations are not enough.
No. Yeah. So super translations are equivalent to the leading one, but each
Right.
the two sub-leading ones are other infinite dimensional symmetry.
Others.
Yeah.
Others.
Okay,
Maybe I can ask a question as well.
excuse me, can
There's
I
time.
just, Gabriele, unfortunately, I have to run, so can you please take
So
over?
I take over for the discussion now.
Yes. Thank you very much again, Monica.
I will try to run the discussion. Yes, I know you have to go. And by the way, Alok may be late, so we continue the discussion on Monica, and maybe Alok will join us a little bit later. Okay?
I'm here, Gabriel.
Oh, you are here. You made it. You made it.
I made it.
Very
I made it.
good. So, but anyway, let's have this question to Monica, and then I don't know, whatever. I mean, we can go on with Monica. Can you stay on, Alok?
Yes, I am here.
Or is it too late for you?
No, it's not. It's not.
It's not. Okay, so we go on a little bit with Monica, and then when we are through with her, we switch to you. Okay, please.
Gabriele, your camera is off, so.
Oh, my camera is off.
Yes.
Okay. I'm not so beautiful.
Okay.
You can stay. Okay.
So may I ask now?
Yes, Alex.
Oh, you hear me? Yeah, great. Yeah, sorry about the concrete mixer outside, if you hear it. Anyway, yeah, I was just wondering if you could return, Monica, to those slides where we were showing the factorization of the IR, and just comment maybe on how that would look in DIMRAG and what that zero would, how that zero would come about in DIMRAG. Could you maybe explain that to clarify?
Yeah, so in DIMRAG, basically, okay, right, so good. Let's see, I written. Yeah, okay, so this is what you get if you had sort of hard cutoffs on both sides. If you're working in DIMRAG, instead you're gonna find, oops. Uh, 1 over epsilon. And so this is to say that, right. Right. So if you have, like, okay, you can then write this if you like. So, sorry, it's.
Maybe I can say something. So it's in DIMRAG, it just says that at any loop order and for a gravitational amplitude, the IR divergence is given by exponentiation, the divergence of the one loop amplitude. So what you get in the exponential is 1 over epsilon times the gravitational cusp. And for people who know the arcsinges, I mean, in the gravitational cusp for GR, like the arcsinge is in the cusp is exactly this arcsinge over sigma squared minus 1. So that's why you see this arcsinge all over the place for the classical gravitational scattering. So that's maybe for some people who are more familiar with that.
Okay, but what
Right, but you still
the question of Alex?
get 1 over epsilon, right?
Which was your question, Alex? I didn't understand. You asked about the 1 over epsilon?
Well, yeah, I mean, now it looks like you have an exponential of 1 over epsilon, where epsilon goes to 0. And
yes.
It doesn't look like very much like a 0.
Yeah, in fact, it goes to 0. As epsilon goes to 0 with the right sign, it goes to 0.
Oh, right. Yeah, it's just a sign issue of where
it's a sign issue.
You have to be careful with the sign.
Below 4D, it goes to 0.
Yeah, okay.
Also, if I may add one thing, I guess if you want to include the other cutoff in the game, you will have something like lambda to the -2 epsilon divided by -2 epsilon, something like that. So that, of course, as epsilon goes to 0, you become independent of the lambda. You just have this 1/epsilon pole that Monica wrote down. But yeah, in principle, you also have the other cutoff, of course, because if you write down this integral in dim-reg without any cutoff, it's just 0, right? It's scaleless as it is written down. So of course, you need at least one other cutoff to have it.
Right. Yeah. Yeah.
Or either that or some other momentum that you have in the game in order to make, yeah. No, I think it's not like that. It's something like that cutoff to the epsilon. So it's not a minus. It becomes a log of the other cutoff. I'm reading what you just wrote down. Sorry. Yeah. Okay. You can think of it like that.
Right. Okay. Yeah. Thanks.
Okay. Other questions? Perhaps, Monica, I will ask one. I mean, to remove the infrared divergences, you have to integrate, I mean, you have to add soft gravitons in these cases, which make up for some finite energy. I mean, in other words, your infrared cutoff is replaced by the resolution of your apparatus. So you get a delta E, where delta E is the total energy in the radiation. So, I'm a little bit worried about the fact that you seem to talk about exactly zero energy gravitons, or you can allow a little bit of energy.
Right. So only the part.
Redefine it. Sorry.
The only part that's constrained by symmetry is the zero frequency part. So this was why the dressings could involve sort of contributions from soft gravitons, where the only part that was really constrained was the zero frequency part.
That's right. But then you say, okay, you extrapolate then the behavior to finite omega, integrate over omega, and you get some delta E.
No, I'm just saying that, okay, maybe I'm misunderstanding your question, but
what I'm saying is that you cannot get rid of the infrared problems unless you integrate over omega on a finite interval.
But it is only the pole that matters. I mean, it is the residue of the pole that is fixed by the symmetry. So even if you...
Yeah, sure.
Yeah,
that is
yeah.
the symmetry, but somehow you cannot just say, I only emit zero energy.
No. Yeah, you have the cutoff, but the residue is, if you don't change anything away from the pole, then it's not going to affect the IR structure anyways. The residue is fixed by the symmetry. But you are right that one is to integrate over a finite.
I mean, physically, you have to put some energy resolution, finite energy resolution. But okay, that's only a small point.
So can I follow up something?
Yes, sure, absolutely. Bruno?
Yes.
Is this, yeah, okay, go ahead.
So Monica was able to convince me that the soft modes decouple, basically, if decouple from the rest of hard modes. Would you say that this implies that the BMS charges are trivially conserved? Because in a sense, they are related to the soft modes decoupled from the hard modes.
Okay, good. So let me so I would say, the BMS charges are trivial if they, vanish when they act on physical states. And so if we consider their action, on states like this where we've actually, taken into account or thought about the vacuum degeneracy, right? So, their action on some state, say, and we'll say, so this is, alpha plus the sum over particles in the end state of the soft factor. And so I argued that you can apply this operator, let's say W of alpha prime, and change alpha, which changes alpha to alpha plus alpha prime. And so if I choose to dress them in such a way where I can choose to dress them in such a way, right, where I set this thing to 0. And what
yes,
that actually,
yes.
What?
Yes, that's exactly the point. Yes.
So, say it one more time.
Yes, that's exactly what I'm getting at.
Okay, but wait. So I can do that, and just to be explicit, what you're doing then is you're saying for every particle, K in my out state, I dress it with essentially the soft radiation associated to its change in momentum or something, its momentum. Mm-hmm. But to satisfy the symmetry constraint, all I needed was this thing net to be 0. So I didn't have to choose, the important point was that the difference between the value of alpha in and alpha out was equal to the soft factor. I didn't have to set the charges to be 0 on both the in and the out. So in particular, what I can do is I can choose, so this is the analog of the statement, in Jackson or E&M, that if you think about, the radiation emitted from charged particles scattering, you decide to solve it with a retarded propagator. You can satisfy the symmetry constraint by choosing your end state to have no gravitons in it, and choosing your out state to have alpha equal to the sum over both the in and the out particles. And so what this is saying is that you're sending in some set. So first of all, this is, what we would do at, for example, the analog, and, this is what we would actually do, right? If we were doing this, for example, in E&M, this says we're scattering some charged particles. And then at the end of the day, we're measuring both the charged particles that come out and the radiation. And so, and this object is not annihilated by the charges. The charges carry non-trivial values for both the in and the out state, which must match.
Yes.
And I
okay.
say the original way where you choose to set the charges to 0 was the one that Pate and Coolish. That's what the original Pate and Coolish dressings do. But it's subsequently shown that, yeah, you don't need it to dress that way, and you can still obtain infrared finite S matrix elements by dressing in this more general way.
Okay, I see. Thank you.
Other questions?
Maybe another short one. Yeah, it's again to that slide with IR in the exponential. So in QED you have the whole same story, right? Mm-hmm. And so we just realized that it's very important that there is a sign that is such that this whole thing goes to 0, not to infinity, when epsilon goes to 0. So I was just wondering if in QED there's a way for charges to get into the mix and spoil that. It depends on what the sign of the coefficient is in front of that, in the exponent there.
Yes, but also, so roughly the replacement for QED is that one of these things gets changed into a Q.
Yeah, but then kappa becomes Q. Yeah, a charge.
Yeah, kappa becomes the electric charge.
Right, and they can be of different signs. So,
well, Q can be of either side. Yeah,
Q can be of either sign, but okay. First of all, let me point out that there's another Q
yeah.
here, and you can show that no, for things that I think, I mean, no, you can show that it's of definite sign and vanishes.
Yeah, Weinberg proves that.
Oh, okay. Yeah, but it's
always the right side. The right
so
sign.
The charges get into the mix, but they always get right.
Probably you have to use charge conservation in the process.
Oh yeah.
Yeah. I think momentum conservation in gravity is replaced by charge conservation. That's what Weinberg.
And then you get always the good sign. Otherwise, amplitudes would blow up instead of going to 0.
Yeah. So that doesn't happen.
That was your worry. No, that doesn't happen.
Okay, great. Thanks for the clarification.
Whereas you see the real production always comes with a positive sign because it's it's a cross section. So that will that's why you need the real Bremsstrahlung to compensate for this effect. One comes with one sign and the other comes with the opposite sign. Other interventions. We can also ask questions to Alok if you prefer, and go back and forth. In any case, it's the same subject, so we don't have to.
Maybe I can ask one more question to Monica. I mean, it's not what you talked about, but like related to this QED question, we know in QED, like, or in QCD, when you have massless particles around, these soft factors get quantum corrections. So what's the status of the quantum corrections or the quantum deformations of these symmetry algebras? Because at the moment you just talked about kind of mostly classical level. Okay, in gravity, you know, the leading soft factor doesn't get corrected, subleading gets only corrected one loop, and so on and so forth. But so in QCD or QED with massless particles, that's not the case. They get quantum corrections.
I think the honest answer is that not a whole lot is understood. Hello, do you have something more to say?
Yeah, I mean, I think in the QCD case, even the leading soft factor is corrected, right? So you get a log omega by omega correction by the infrared divergences in QCD because of the color, divergence of color. So
even in QED, if you have massless particles around.
Yeah, even QED with massless particles, right. So I think that it's not, as far as I understand, it's not understood how to. And at every loop order, you get more and more infrared divergences, right? I mean, higher and higher infrared divergences. So even the Weinberg soft factor is not stable under loop corrections in, as you say, massless QED or QCD. But on the other hand, there is the hard soft collinear factorization, which is in QCD, which is kind of universal, right? So I don't know, maybe there is a symmetry understanding of this factorization theorem, at least, which was proved by Schwartz a few years back.
But the factorization just says that you do have a soft factor times a hard amplitude, right?
Yes.
Yes, that's what we would expect from the word identity also. So I think that there could be. I mean, I don't know if anyone has related it to symmetries, but the fact that there is a universal factorization kind of hints at some sort of a symmetry argument explanation, maybe.
Well, what is known is that in QED and even worse in QCD, of course, there are collinear divergences on top of soft divergences.
Yes.
And those can be factorized. There are factorization theorems and so on. That's the basis for the Parton model, for instance, in QCD. But it is believed, and actually goes back precisely to Weinberg's paper, that there are no such collinear divergences in gravity.
In gravity, yes.
So you can safely take the massless limit. I'm talking about the hard particles. They can be massless, and Weinberg shows that there is no infrared divergence. And in fact, he comments on the fact that it would be a disaster if the electron were massless, because then things will blow up. Or if any charged particle were massless, that would be a problem. But no, I think for gravity, as far as we know, everything is fine. This is why we were very worried, Enrico, when Bern came up with a result which seemed to blow up in the massless limit.
Yeah. For gravity, I completely agree with you. There are no collinear divergences. No. My question was, my question was about QED or QCD.
QED. Okay.
But in QCD also, because there is a factorization between soft and collinear now, so there collinear, of course, I don't think we expect it to come from any symmetries, but I think the soft factors maybe that will be.
Well, the collinear divergences in QCD should be much more complicated, right? Because ultimately you have to, I mean, ultimately that's a question of how you define your Parton distribution functions.
Exactly.
Right? And I mean, there's this whole question about factorization violation terms due to like these Klauber effects and things like that. So I think in QCD, it's like very, very complicated.
Yeah. No, but now that they have been disentangled, I was thinking maybe because the soft and collinear factors have been disentangled by Schwartz, so maybe the soft factor could have some symmetry interpretation. I don't think it has been investigated.
Yeah, in QCD, you know that your quanta are not really the asymptotic states of the theory, even. So something terrible must happen if there is confinement. But your question, Enrico, was whether there is a symmetry as.
No, my question was, so for QED, when we know from the soft theorems that they do get quantum corrected, like my question was, what's the analog of that? Like, what's kind of the quantum deformation of the symmetry operators or this asymptotic symmetry?
So in QED, in the massless QED, maybe I can say one thing based on the work of Ashok and Vishwajit, that the one loop, the soft theorem is one loop exact. So there is this log soft theorem that they derived, which is also valid in the massless QED limit, and that doesn't receive any correction because of two loop infrared divergences. So there is a universal log soft theorem in QED.
So that's for quantum QED or for
quantum QED? Quantum QED. Okay. Yeah. So the idea there is that they use Grammariani technique, and they show that, I mean, even if you have the amplitude which is infrared divergent, the ratio of the amplitudes is infrared finite, and that gives you the soft factors. And so you have the Weinberg soft factor, which is the leading, and then you have a logarithmic soft factor, which is the next one, which is one loop exact. It doesn't receive any other corrections, and it's universal then also, like Weinberg soft factor. It only depends on the asymptotic momenta of the charged particles.
And in gravity,
it's the same in gravity. There's an additional contribution in gravity because of the fact that even the soft graviton experiences the gravitational drag. So there's one more term, but there is again a one loop exact soft factor which goes as logarithm of the frequency. So yeah. I think one thing maybe I can say is that even
but sorry, even
yeah,
even in QED, if you have
yes,
massless states around, like you can think of like even even the photon, right? Like you can have like loops of massless particles that like
yes,
the photon still interacts like secretly with its
yes,
like with other photons. So like, okay, so
yeah, but
why is this?
yeah, they do not, as far as I understand, they will contribute to higher order in the soft expansion, you know. So if you go to the log omega expansion, which is the subleading expansion, then they do not affect. So now they have, I think Ashok's student Vishwajit, he has derived the omega log omega squares of photon theorem, which gets contribution at 2 loop, it's the 2 loop infrared divergences. But it's 2 loop exact, so you don't get anything from after 2 loops. So at each loop order, you have a new soft theorem now, which is universal, which does not change under if you add other operators or anything. So, and yeah, it's not clear how they are all related to symmetries, but they are stable under corrections.
Yeah, but that's interesting. So there must be some sort of power counting argument. Like in gravity, like this non-renormalization is trivial because of the dimensionful coupling constant, right?
Yes,
because kappa is a mass dimension. So there, you're saying there is like there must be some similar power counting argument for why these higher loop, like QED corrections, then also remain stable somehow.
I think it is there in Ashok's paper. I mean, if you look at his paper on the logs of theorem, there is an argument.
Okay. Yeah. Cool. Thanks.
Sorry, just a follow-up question to see if I understood. So in the massive QED case, the 1 over omega term, the Weinberg term, is perfectly fine, right? Even at the quantum level, is it correct?
Yes.
Then then one can ask what happens if you send the mass to 0, and then you're saying in that case also this 1 over omega term receives a contribution log omega over omega.
But no. If you take massless, I mean, I think in QED, even in the massless limit, unless I'm mistaken, I think 1 over omega is a universal factor. I don't think it gets corrected. There is a correction at log omega order, which is subleading to 1 by omega. So the log of omega I was talking about is only I was talking only in the context of QCD, where because of the color emission, you get a further correction. Every loop you get a over dominant correction to the Weinberg factor,
including the leading one.
Including the leading one, but in QED, I even in the massless limit, I don't think you get any correction to the leading one. You just get higher and higher.
Sorry, but in the massless limit, it's a little unclear in QED, right? Because I can think about like, so how do you compute it, right? You compute it, you put the charged particles as Wilson lines. So you can think about it like in QED where you have massless states running. You can think about a diagram where you have 2 Wilson lines like QI and QJ. They straddle three photons, and the soft photon gets emitted. So that would be what, 3 loop, 4 loop correction to the soft emission, emission.
Yes.
So and that's at leading power. That means that 1 over omega. So I think it's still unclear.
So if you maybe you're talking about exact massless. I mean, if you take massless.
Yes, exactly. Yeah. Once you give masses, then it's clear, because any internal massive fermion loop or whatever particle loop you have, you can integrate out to generate effective operators like f to the 4 or something, or f cube, which are completely power suppressed.
Okay.
Which are power suppressed in the soft momentum, and then you can count. But if you have exactly massless particles, then you cannot integrate them out.
Then yes, I agree. I do not know, but in QCD, even without, I mean, just in ordinary QCD with massive colors, I think you get an infrared correction to the Weinberg factor.
Yeah.
So it's more severe in that sense.
Yeah, I mean, there's like NF. Yeah, you have NF terms and stuff like that. Yeah. In QCD, the soft emission function gets much more complicated, because ultimately it just couples more and more. It couples more and more legs together. And so it's like a 2 loop in QCD. Like with Lance, we calculated the 2 loop soft emission function at leading power, And there you see for the first time you can couple like 3 hard partons together, and then yeah, you get contributions from that stuff too.
And that dominates over the Weinberg soft factor. You get a contribution which is even more divergent than the Weinberg factor.
What do you mean it's even more divergent?
I mean, it goes log omega by omega to some power, not like 1 by omega.
Okay. Other questions or? Perhaps I have one question myself, but it's a little bit outside of the of the subject. I mean, it was once claimed by Strominger, Hawking, and Hall that this soft radiation can carry a lot of information and solve the information paradox. Does anybody know what is the status of that claim? I know it, it provoked a lot of debate, but I don't know what is the present consensus on that. If nobody knows, we'll ask Strominger next week. This is a little bit related to my question about getting rid of the infrared divergences. If one really talks only about zero energy radiation, how much information can it be there if you don't give any phase space? Okay, nobody dares.
I mean, I'm sure the speakers of today are know much more on this than I do. But since nobody is answering, I can try to say what I know. Okay. So, for instance, people have been looking at effects related to supertranslations inside Hawking radiation. So, for instance, what happens if instead of characterizing your asymptotic state just by the angular, omega ln in the scalar, toy model that also Hawking has in his original paper, you add the supertranslation charge as an additional quantum number or a vacuum label that you add to your states. And basically, if you redo Hawking's calculation, you find that the eventual effect on the spectrum is non-existent. So eventually, the spectrum is still thermal and is still a delta of LL prime, MM prime, and no, and then the thermal distribution, of course, the Bose-Einstein without any leftover. Sorry?
No hair, no hair.
Exactly, without any leftover dependence on this T of the angles function that parameterizes supertranslations. Recently, in a paper with another collaborator at Nordita, we tried to see if that could be improved, and we also try to see what happens for super rotations, which are analogs. These symmetries that also Alok was introducing, and there you can have effects, but in the end there are singularities, because in particular we looked at these Barney-Strassar super rotations, which of course have pole in some direction on the celestial sphere, maybe associated to some cosmic string in the bulk and so on. So in that case, you can have effects also on the spectrum, which is somehow interesting and also expected, because for instance, if you boost a black hole, which is a special type of super rotation, you expect to see at least the boosted black body spectrum, right? And that, of course, you also get more non-trivial stuff for these generalized boosts, so these super boosts or super rotation symmetries that people have considered, but you also get some singularities. Remarkably, the spectrum itself, so dn over the omega or d over the omega, is finite as long as you do not look in the direction of the singularity itself. But the integrated energy emission, of course, diverges for these. So if you integrate it over the whole, in all directions. This is my 2 cents on this, I guess.
Okay, thank you. Well, that's interesting. Okay. Anything else? I think it's 7 o'clock here. So there are no more questions. I think we can close the session. I think it was an interesting week with lots of exchanges. So I take the opportunity to thank all the speakers and all the participants. And well, I hope to see you all next week, where we will have, you know, more general talks, and especially the weeks after, because I think that's when we can really get together and have discussions, even in small groups and so on, maybe establish collaborations, maybe make progress on some of these problems. So have a nice weekend and see you soon. Bye-bye, everybody.
Thanks,
Bye.
bye.
Thank you.
Bye.
Ciao Gabriele, ciao a tutti, bye bye.